Catenary cable. A uniform cable suspended from two points for example A and B, and hanging under the action of its own weight only. We will show in this limiting case that the cable assumes a curved shape known as catenary. The cable assumes a curve This picture provides an example of a catenary cable. The free body diagram of a finite portion of the cable of length S measured from the origin is shown in the picture here. This free body diagram differs from the ones with the external forces, that the total vertical force supported is equal to the weight of the cable section of length S rather than the load distributed uniformly with respect to the horizontal, as shown in this picture. If the cable has a weight mu per unit of its length, per unit, its length, the resultant R of the load is mu S. And the incremental vertical load in the distributed forces replaced by this force. We had before that the equation for the cable shape can be calculated from this relation. For the In this case, we have this relation for the W is ds on dx. So we can continue the relation. We know that ds for a ds one plus so we can rewrite the relation as this expression. Square. This equation is the differential equation of the curve formed by the cable. This equation is easier to solve if we substitute the relation P equals to dy on dx. So dp on dx one plus p squared. So we can rewrite the relation as this expression dp dx. We're making an integration ln p plus x plus c. The constant c is 0 because dy on dx p equals to 0 at x equals to 0 according to this picture. So c equals to 0. The relation can be rewritten as this expression divided P or ln hyperbolic sinus where the hyperbolic function is introduced for convenience. The slope may be integrated to obtain cosinus hyperbolic plus cos. At this equation is the equation of the curve catenary formed by the cable hanging under the action of its weight only. From the free body diagram, we see that from this picture, tangent theta this angle is US on T 0. Thus, from the previous expression for the slope, we have the S T 0 we obtain the tension T in the cable from the equilibrium triangle of the force. So we have this relation T square one plus sinus hyperbolic square x on T0, which is equals to T0 square cosinus T equals to T0 cosinus hyperbolic. We may also express the tension in terms of T0 plus 1 mu y. These equations show that the change in cable tension from that at the lowest point depends only on the term mu y. Most problems dealing with the catenary involve solution of the expressed equation, which can be handled by a graphical approximation or solved by numerical solution. A procedure for a graphical or computer solution is illustrated in some example. The solution of catenary problems where the sag-to-span ratio is small may be approximated by the relations developed for the parabolic cable. A small sag-to-span ratio means a tight cable and the uniform distribution of weight along the cable is not very different from the sum load intensity distributed uniformly along the horizontal. Many problems dealing with both the catenary and parabolic cables involve suspension points which are not on the same level. In such cases, we may apply the relations just developed to the part of the cable on each side of the lowest point. Another distributed force, fluid statics.